In this video, we will do some more derivative examples. So the first example I want to look at has these two functions, r of x and t of x. And it asks us to find all x values where the tangent line to r is parallel to the tangent line to t. So I want you to first pause the video for 1 minute just to think about how you might get started with this. 4, 3, 2, 1. Pause it for a minute, just thinking about what the key idea might be on how to begin. All right, so hopefully you did that. Hopefully you paused it for about a minute to try this. So let's talk about it now. So it mentions that these two tangent lines need to be parallel. And lines are parallel if they have the same slope. Let's write that better, same slope. All right, so we are going to need the slope of the tangent line to r to be equal to the slope of the tangent line to the function t. And we know the derivative tells us the slope of the tangent line, so r prime of x is going to be the slope of the tangent line to r. That needs to be equal to t prime of x. That'll be the slope of the tangent line to t. So let's take those derivatives. So we're going to use our derivative rules for this. So for the 1/3 x cubed, that 3 is going to come down. Remember, when I have a constant like a third multiplying my function, I can keep that constant there. I'll get 1/3 times, now use power rule, 3 comes down, and I get x squared, subtracting 1 from the exponent. If I do the same thing on the next term, I can keep the 1/2 there, and then multiply by the derivative of x squared, which is 2x to the 1. And then for minus 6x, I would get that derivative is minus 6. Technically, the power of the x is 1. And if I did the power rule, the 1 would come down, and I would get 1 times x to the 0. And then the derivative of 5 is 0, because that's a constant. All right, so before I do the derivative of t, let's simplify this. So 1/3 times 3, that's just 1. I'll get x squared. And then the 1/2 and the 2 cancel, and we'll just get x. And then I get minus 6, and then x to the 0 power, that's just going to be 1. So that's going to be equal to. Now let's do the derivative of t. And this one I'm going to do more quickly. As we do more of these, I'll start to up the speed a little bit on how we do these derivatives. So this 4 is going to come down. That'll cancel the 1/4. So that'll just give me x to the 3rd, subtract 1 from the power. Next, for the next term, the 3 will come down, cancel the 1/3, and I'll get plus x squared. And then for the next term, the 2 will come down. It'll cancel that 2 in the denominator. So I'll get minus 3, x to the 1. So I can just write x. And then for the last term, that minus 6x, that derivative is going to be minus 6. Okay, so let's just copy that here as well. X cubed plus x squared minus 3x minus 6. Okay, so I notice that some of the terms on both sides cancel. This minus 6 is going to cancel from the left and from the right. And the x squared is going to cancel from the left and from the right. So now we need to solve this equation. And I want to do it in 2 ways. First, I'm going to do it incorrectly, because I want to show you a common mistake people will make with equations like this. And then after that, we'll do it correctly. Okay, so an incorrect method and a correct method. Okay, so first, let's do the incorrect method. If I add the 3x to the left, I will get 4x equals x cubed. All right, and now let's divide both sides by x. So 4x over x will be equal to x cubed over x. And that gives us 4 on the left and x squared on the right. And if I square root both sides of this equation, I'll get x equals, I got to put a plus or minus when I square root both sides, x equals plus or minus 2. But there's a problem with this. There's another answer to this equation. Can you see what it is? I'm not going to officially count it down, but I'd encourage you to pause the video for about 30 seconds to see, can you figure out what that other answer is that we just didn't get? There's something I can plug into both sides that makes them equal. All right, but it turns out x equals 0 does the trick. X equals 0 also works in this equation. So that also works in this equation, which leads to the question of why did we lose an answer? So we lost an answer because when we did this step, where we divided both sides by x, there's a problem if x is 0. Because if x is 0, I can't divide by it. And that's exactly the answer that we missed. We missed x equals 0. So the moral here is never divide both sides of an equation by a variable. Because if we do that, we can lose solutions. We can lose solutions if that variable could be 0. All right, now, so that was the incorrect method. What's the correct way to do this? So anytime we're tempted to divide both sides of an equation by a variable, what we should do instead is move all the terms to one side, so the other side equals 0. So if we did that, we'd get 0 equals x cubed. Let's move this x to the right, minus 4x. And now I can factor that term that I wanted to divide before, the x. If I factor it, I'm left with x squared minus 4. And that factors more. This is x times, that's the difference of squares, x minus 2 times x plus 2. So now I can see that x equals, from the x term, 0. From the x minus 2, it could be 2. And from the x plus 2, it could be negative 2. So I get these three values, and though that is my answer. Now I have all the solutions. Remember, the problem wanted me to find the x values where the tangent line to r is parallel to the tangent line to t. We set the derivatives equal, because those tell me the slopes of the tangent lines. And I figured out all the x values where those derivatives are equal. All right, let's do another example. So this example, it says g of z is 3 times z cubed minus 2, that whole quantity squared. And I want to differentiate g of z. Differentiate just means take the derivative of. Take the derivative of, in this case, of g of z. So seeing that I have this whole thing squared, it might be tempting to say, oh, can't I just use the power rule and bring that 2 down? But I have to be careful. The power rule works it would work if I had 3x squared, if it was just like my variable being squared, but it doesn't work for 3 times some more complicated stuff being squared. Okay, so for stuff like this, we'll eventually learn a rule for this. It's called a chain rule. Chain rule, and that is in section 3.4. So using our current methods, we can handle this. So using our current methods, we must first simplify. Okay, so we have to first simplify. So we have g of z equals 3, and then that z cubed minus 5 squared, sorry, minus 2 squared, that means z cubed minus 2, whoops, let's write this better, z cubed minus 2 times z cubed minus 2. And now let's multiply it out. This is 3 times, if I distribute those terms, I'll get z to the 6th minus 4z cubed, and then plus 4. So we end up with this. And I could either start to take the derivative right now. Whoops, let's write g of z here. And just do the constant multiple rule and keep the 3 multiplying the derivative of everything inside the parentheses. Or I could distribute the 3 and then do the derivative. In this case, I think distributing the 3 isn't too bad, so let's just do it. We get 3z to the 6th minus 12z cubed, and then plus 12. So now if I do the derivative, we'll get g prime of z. Maybe let's put this in a different color. We'll get g prime of z equals, bring the 6 down. That gives us 18 z to the 5, subtracting 1 from the power. And then bring the 3 down to get minus 36 z squared, once you subtract 1 from the power. And then 12 is a constant, so its derivative is 0. So that's my answer. So the key idea here is, based off of the rules we just have, like power rule, constant multiple rule, sum and difference rules, if we run into something that I just can't use one of my rules on, like in this case, I have some complicated stuff being raised to a power, we need to try to simplify it first, like we did here. In terms of our goals for this section, we finished goal 3, to do some more derivative examples, and we upped the difficulty a little bit in this last video.